When most people begin programming microcontrollers, they start with a simple infinite while loop. The idea is straightforward. Keep checking inputs, perform actions, and repeat forever. For example, you might read a sensor, update an LED, and then wait a little before doing it all again. This approach works well for very basic tasks, but it quickly shows its limits. Suppose you want to read a sensor every 10 milliseconds while also blinking an LED once a second and sending data over UART occasionally. In a single while loop, these actions compete for time. If one function takes too long, everything else gets delayed. You might miss sensor events, or the LED might blink irregularly. The while loop method is fine for hobby experiments, but as soon as projects grow more complex, timing and responsiveness problems appear. That's why embedded systems need better solutions. Let's think deeper about the problems with using only a while loop. First, microcontrollers often need to respond to real-world events that happen at unpredictable times, like a button press or a sensor trigger. If the loop is stuck in a delay, the event might be missed completely. Second, tasks with different timing requirements can interfere with each other. For instance, fast sensor readings can be delayed by slower operations like writing to a display. Third, debugging becomes harder as the loop grows into a messy chain of if statements and delays. Finally, such designs don't scale well. Adding more features makes timing conflicts worse, and the system becomes unreliable. In short, a pure while loop design locks you into a sequential mindset where one thing happens at a time, even though the real world requires handling multiple events simultaneously. To overcome the rigidity of while loops, microcontrollers provide interrupts. An interrupt is like a phone call to the CPU. Whenever a critical event occurs, such as a button press or a timer firing, the CPU pauses its current work and runs a special interrupt service routine, ISR. Once the ISR finishes, the CPU returns to what it was doing before. Interrupts make systems more responsive. For example, you don't have to constantly check a pin to see if a button is pressed. The ISR will run instantly when the event happens. However, interrupts also have downsides. They should be kept short, because long ISRs block other interrupts. Handling many interrupts quickly becomes complicated, especially if tasks share data. So while interrupts improve responsiveness compared to a plain while loop, they don't solve the bigger problem of managing many long-running tasks in parallel. Interrupts are powerful, but they aren't a complete solution. Imagine a project with multiple tasks: reading sensors, sending data over Wi-Fi, updating a display, and logging to memory. Each of these could use interrupts, but writing and debugging the code quickly becomes overwhelming. Interrupts don't inherently manage priorities across tasks, so deciding which task should run first is left to the programmer. Also, ISRs can't handle long operations since they block the CPU. That means you often need to push the work into the main loop anyway, which brings back earlier problems. Sharing resources between interrupts and normal code also risks race conditions and unpredictable behavior. In other words, interrupts are great for urgent signals, but we still need a high-level system to coordinate tasks, manage priorities, and ensure timing consistency across an entire application. This is where real-time operating systems step in. An FreeRTOS, or real-time operating system, provides a structured way to manage multiple tasks on a microcontroller. Instead of juggling loops and interrupts manually, an FreeRTOS gives you tools to define tasks, assign priorities, and let the system decide when each should run. The real-time part means the system can respond to events within predictable time limits, which is essential when dealing with sensors, motors, or communication protocols. For example, one task might read sensor data every 10 milliseconds, another might maintain a Wi-Fi connection, and a third might update a display. With an FreeRTOS, all these tasks can run smoothly without blocking each other. It also provides inter-task communication, timing services, and synchronization tools that make projects far more scalable. In short, an FreeRTOS turns a messy, hard-to-maintain codebase into a professional multitasking system. FreeRTOS is the most widely used real-time operating system for microcontrollers. It's free, lightweight, and highly portable, making it perfect for resource-constrained devices like the ESP-32. The FreeRTOS part means it schedules tasks predictably so deadlines aren't missed. Unlike desktop operating systems, FreeRTOS is extremely small, measured in kilobytes instead of gigabytes. It provides everything you need for multitasking, task management, scheduling, timing functions, and communication primitives like queues and semaphores. Best of all, when you use the ESP-IDF framework, FreeRTOS is already included. In fact, every ESP-IDF program you write is running under FreeRTOS, even if you don't realize it. Your familiar app_min function is just one FreeRTOS task created automatically. Understanding FreeRTOS unlocks the full potential of the ESP-32, letting you design professional, scalable IoT projects that handle many operations smoothly and predictably. In FreeRTOS, a task is like a mini program running independently inside the ESP-32. Each task has its own stack memory and priority level. This separation means tasks don't block each other the way functions in a single loop would. For example, you could create one task for sensor readings, another for Wi-Fi handling, and another for logging data. Each task would run as though it owned the CPU, but in reality, the scheduler ensures they share time fairly. Tasks can be suspended, resumed, or delayed, which makes timing much more predictable than using delay in loops. Because tasks are modular, they make your code easier to debug and extend. If you need to add a new feature, you simply create a new task. This modularity is one of the biggest advantages of moving from while loops and interrupts to a full FreeRTOS environment. The scheduler is the brain of FreeRTOS. Its job is to decide which task runs at any given moment. FreeRTOS uses a priority-based preemptive scheduler. That means tasks with higher priorities will always preempt lower priority tasks when both are ready to run. If multiple tasks share the same priority, the scheduler uses time slicing, where it switches between them fairly so that none is ignored. On the ESP-32, which has 2 cores, the scheduler can even run tasks on separate cores simultaneously. This makes multitasking highly efficient and predictable. For example, if your Wi-Fi task is priority 3, your sensor task is priority 2, and your LED blink task is priority 1, you'll know exactly how they will be scheduled. This predictability is what keeps ESP-32 projects stable, even when handling heavy workloads. In a multitasking system, tasks need to talk to each other safely. FreeRTOS provides several tools for inter-task communication and synchronization. Queues let one task send data to another without conflicts. For instance, your sensor task can place readings in a queue, and your logging task can pick them up later. Semaphores are used to control access to shared resources, such as a UART port or SPI bus, preventing two tasks from using it at the same time. Event groups allow tasks to wait for specific conditions, such as Wi-Fi being connected, before continuing. These mechanisms eliminate the need for risky global variables and polling loops. Instead, they provide structured, thread-safe ways to share information. Mastering these tools is crucial for building robust IoT projects where tasks cooperate efficiently and avoid data corruption or timing conflicts. Let's recap what we've learned. We started with the basic while loop approach, which works only for very simple tasks but fails when systems grow complex. Interrupts improved responsiveness, but they alone couldn't manage multiple long-running tasks or provide priority control. That's why microcontrollers benefit from an FreeRTOS. FreeRTOS is the most popular real-time operating system in the embedded world, and it's already built into the ESP-IDF framework. We learned that FreeRTOS uses tasks, each with its own stack and priority, and that the scheduler decides fairly and predictably which task runs. We also covered context switching, communication tools like queues and semaphores, and the importance of designing with modularity and scalability in mind. By now, you should see that FreeRTOS is the foundation for building professional IoT projects on the ESP-32. In the next lessons, we'll create tasks ourselves and explore how priorities affect real applications.